Good evening and welcome everybody. This is Obi-Wan Pets for Simplex Pachinko. Starting a bit late tonight just because I was trying to get my other box working, but unfortunately it does not want to cooperate tonight. No surprise. Last week it just wouldn't work, and today it decided that whatever I tried to install just was going to cause a fatal error, and yeah, couldn't get it back. So, of course, just had to reinstall Ubuntu. This is the third time now that I've done it, so well, can do something. Alright, so generically, mathematicians like to think of sets individually as some sort of like ellipses or circles that have items in them. So elements of the individual sets. We'll call this one set A and this one set B. So any particular values here are all going to be some A belonging to set A. And over here, these are all going to be some B values belonging to set B. So overall, you get this idea that individual elements of the sets are going to be found within their individual sets, and gotta trade stuff around over here. It can be. Alright, so with sets A and B, then we want to look at like what are the individual relationships that exist between elements of these sets. At the moment, they appear to be all disjoint. So if they're completely separate from each other, my handwriting's deteriorating. So for us, it was only a 200, being 100 being standard college level, 200 being second year. And that was the same at University of New Hampshire as well. So it was a second year course intended to be taken as a sophomore. Alright, so no A's and B and no B's and A, then these are going to be disjoint from each other. Well, no. I mean, the numbering system really doesn't mean anything in terms of that. It is mostly just like when you should take it. Okay. So some of the other relationships that we could have involve drawing out like Venn diagram type things and saying, okay, here's set A, here's set B. What kind of relationships exist between these things? Very generically, yes, but like for us, right, our statistics class and our pre-calculus 1 classes are like almost the same number, but realistically they are very different types of mathematics. So pre-calculus is going up this particular track. You're almost always going into calculus at some point, but if you're taking statistics, it's just a very different sort of feel to it. I personally found statistics much more difficult than any of the algebraic stuff. I mean, maybe, but at the same time, all of ours, right? Multivariate calculus, linear algebra, and differential equations all have numbers that are, like, again, approximately the same as each other. That doesn't necessarily mean that their relative difficulty is going to be, scaling based on their number. And a lot of people find Calc 2 way harder than Calc 3, which, again, in ours is Calc 2 is our series and sequences, and integration techniques. So that was mostly what you just took. I didn't find differential equations terribly difficult, but I was also, again, very algebraically minded, and so if you given me like a process or a formula to sort of follow, then I could breeze through it pretty easily. So when we started getting into the stuff that's like, well, we don't know how to solve this, but just try something. That was very difficult for me. So so when we start looking at stuff like this, we're going to say, all right, well, given sets A and B within the universal set, we'll go like that for now. Right, so to get to talk about the individual like relationships that exist here, we start looking at what's going to happen if we want, what is the set A union B going to look like? All right, A union with B, it's just going to be the combination of all of the things. If yep, right, so some N is going to be in A union B if N is in A or N is in B. So where are the acceptable locations of N? And that's going to be anywhere in any of these individual things. It has to be in at least one of them. Okay, and then we want like, what is A intersect B? Okay, so N is going to be in A intersect B if N is in A and N is in B. So in this particular case, it has to be in both A and B at the same time. And so we're talking about the overlap of these two areas, which is going to be all this stuff. This is all logic. So this is determining where something is based on the relationships it has to individual portions. So again, the union is just like an or statement, and the intersect is like an and statement. I mean, we use those exact words in these larger statements. So then in the third example, or I'm doing a third example here, we could say that we want something where we want to talk about A intersect not B. So for this to occur, N will be inside of this A intersect not B. And I interchange this symbol. So I don't know if that's the right thing to do, but whatever. It's cool. If N is in A and N is in not B. I mean, oftentimes. It's math proof, right? You basically have to start from a place of trying to say like, okay, I was just kind of doing whatever I was doing in that last class, and it's not going to work in this class. It's going to be something completely different. How have the rules changed, and how are they the same? I have a decent proof book. I'm trying to remember if I have it here or if it's at school, but what's that one? Yeah, that's it. That's been about 5 years sitting on the shelf doing nothing. How to read and do proofs. I would probably look this up by Daniel Solow, Solow. I would see if your school's library has a copy of it or something similar. It's possible also your community library might have something about that. I mean, you keep saying this, but at the same time, you do okay. Okay. So, the idea here is that our n, whatever it's going to be, has to be within the set A. So here, but then also cannot be within the set B. So this is going to exclude all of this stuff here. Right, can't be within B, has to be within A. So we can see, okay, it's going to stop here. We can't go inside of circle or set B at all. So this stuff is out, which means that now we have to include only this stuff here. Since it must be within the set A, it has to be within that circle and outside of the other one. you tried MIT's OpenCourseWare at all? That's more literal lectures, so the actual lectures from MIT, um, which might do at least okay for getting a head start on it. It's not necessarily going to be like the best way to learn it, but then you can try to look up from there somebody else and be like, okay, who else does a good explainer videos on linear algebra topics? My brother-in-law and his girlfriend were here. I think I picked up something from him. Ugh. So anyway, yeah, I would try maybe look up Daniel Solo, how to read and do proofs, or something similar within the mathematics section of your library. Again, academic libraries are going to be a little bit easier to find stuff like this, but your like local library might have something similar in the 525 decimal number. I think it's 525. I always forget. Well, yeah, but that's what you came here for. You learned all the sine, cosine, tangent stuff from me. Yeah, yeah. A lot of people, as soon as they can make money off of their material, they're going to do it. Me, I earned 13 cents last week. Ayo. Come on. Come on. Oh my god. This computer's so slow now. I swear it's taking it out on me, now that I've gotten a new one. I mean, maybe, but at the same time, like, this is like a thing that almost nobody does. And so, like, if I'm doing a video game, it's like, he's just another guy doing a video game. But if I'm doing math, which I enjoy, right? I wouldn't do it if I weren't enjoying it in the first place. But because I do math, people pay attention and are like, "Oh, this guy does math. Let's." It is true. So the title of tonight's stream, by the way, comes from this book by Sunil Singh, who was at the Amatic conference that I was at. That was a mistake. Anyway. So, Chasing Rabbits, A Curious Guide to a Lifetime of Mathematical Wellness. Both he and Peter Liljedahl, the other guy that I was talking about a few streams ago, we're basically talking about how we need to change the entire idea of teaching mathematics. And we've got to figure this stuff out because there are far too many people who, as you said, Blainland, are just really not interested in like doing anything in terms of mathematics. And it's really a shame because there is quite this wonderful beauty in all of it that just nobody sees because they're too hung up on the fact that they have to do all these memorizations and again, if you're memorizing mathematics, you're doing it wrong. No, 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 no. You don't put that in resumes. You could put that as part of your. You could put that on your, transcript and just be like, see, haha, I took calculus. But it's not going to be like massively upfront. That's the thing, though. It really isn't. It's just that it's got this perception about it that it is. So if we are to kind of dispel this myth that is sitting around mathematics, that it is far too hard for any normal person to understand, we've really got to get people interested in doing mathematics just for fun and thinking about things in a much more in-depth and methodical way to really understand how it is that math as a whole is supposed to be understood. So you can see I'm not terribly far through the book, but nevertheless I am still wonderfully inspired in the first 40 pages by what he said about basically how we should be doing this is like giving students the opportunity to breathe and just go figure something out. Go struggle with math for a bit, come back later, and have the experience that we all wished we had had growing up. Because of all of us math teachers pretty much always wish. No, you can do it forever. You can do all of it as long as you want. So I have until your final exam to inspire you, is what you're saying. Ugh, really? That's just silly. Well, it's a little better anyway. Well, yes, but that's the thing is that, like, in coding, you can come up with ideas of how functions work and all this other stuff, which then relate back to mathematics. I'm not saying you have to necessarily grind math. I'm saying that the way to figure out problems is really what we're dealing with, not just how to do a calculation. So getting you to understand that, for instance, the mere idea of just setting up a problem and thinking about how to solve it is mathematical itself. Alright, so one of the questions that he had, and this was something he worked out with one of his team teachers and said, here's what we're going to do. We're going to give these students a final exam that is not going to have like your standard final exam questions on it. We're going to, for like the last week of classes, sit around and talk about the problems at the end of the book. The ones that you never get to. The cool ones that are like, here are some application problems that are like ways to challenge your students and things like that. And what they did was they came up with 12 problems, 6 from each of the teachers in this team, Sunil Singh and his friend, and said, of these 12, we're going to pick 5, which will be on your final exam. So we're not going to tell you which ones. Of these 12, you're going to have 5 of them. Go. And they said it was the most productive week they'd ever had, because these students were just talking amongst themselves and trying to figure out how to solve things. And so one of the problems was they've got a point P, which is in the in the middle somewhere of a square, and 3 of its sides, or 3 of the distances that get to point P from the corners are 3 and 4 and 5. No guarantees on any angles or anything like that. So again, P could be like here. So this one could be 4, this one could be 3, and this one is not going to be, but possibly could be 5. Right, it's far too long comparatively to the other two, but I think you probably get the point. There are no guarantees on the angles or anything like that. So he had their students working on it and said, "This is one that I think is very interesting. Why don't you all go try it?" And addressing the reader, like, go have a look and come back with it sometime later. So looking at this, I think it's an interesting problem. I don't know that we're going to get anywhere with it, but I thought this is going to be part of his suggestion, is that everybody go and just do the Alice in Wonderland thing of go chase rabbits for a bit. It may very well be sort of a fruitless exercise, but at the same time, it's not going to be a fruitless exercise, because we will have worked at something and struggled and tried to do this mathematics. And just by thinking about the various ways that things can exist here, what kinds of patterns can exist, like, that's really what's at the heart of all of this. Yeah, I mean, the problem is that we need time, and time is not something that we have when you're at school. Ideally, everyone would just put down their damn phone and do some work, but, I can be a crotchety old man some other time. Megalomorph would agree with me. Nope, that's not what I wanted. Alright, so the goal of this was find all possible values of the side lengths of the square. All right, given the only information that you're going to have 3 and 4 and 5 to 3 of your diagonals. This being a square, we can say, well, it's going to generalize to pick any one pick any one corner that you're not going to get to, and it doesn't matter if it's corner 1, 2, 3, or 4. It's going to be symmetric going all the way around. So if we find all the solutions on this particular square, we'll find all the solutions for all particular squares that we get. So it doesn't, in fact, matter where we put point P on the interior of the square, as long as it's in the interior of the square. And again, three of the diagonal lengths, these are not diagonals, 3 of the lengths to the corners from P are going to be 3 and 4 and 5. So we got a few different ways that this could work. So if we just think about it like logically, right? If we put a circle with radius 3 around a particular point, all right, this is going to be corner 1. And if we put another circle with radius 4, that needs to be bigger, around one of the other points. And again, without loss of generality, it doesn't actually matter which way this goes. And then we put a circle with radius 5 around the third point. Yeah. Okay, we can put a bound on this. So if it's in this particular order where we get 3 and 4 and 5 like that, then we've got to get individual points where all 3 of our circles are going to intersect with each other, right? That's basically what we've got here. So we've got a circle around each of the corners whose radius is going to be hitting this point P. And it's all perfectly lining up. All right, so what we don't know is how far it is between any two centers, except we have bounds. So, for instance, if our 3 and 4 are going to be along one straight line, then this has to be less than or potentially equal to 7. Alright, the side length can be 7. We could have done the same here, but that just means that this is going to be less than or equal to 9, which, again, this supersedes that, right? We, of course, have to have it be less than or equal to 7. Alright, one sec. So, like, good? Okay. So, one of the ways that you can bolster that is by doing Project Euler. Now, most of it is mathematics based, but nonetheless, Oy. This is mathematics based, but it gets you an idea of, again, how to solve individual problems. Yeah, and finding tutorials for Java and Python. Trying to find... This is one of the other things, right? Like, sure, get individual skills. But I think most of all, what you're going to have to do, Blainland, is find a project. A small project, but a project nonetheless. And work at it. And fail miserably many times. But keep working at it. Just whenever you have some time. Like something small, not like solve the problem of whatever, I don't know, not come up with a new encryption algorithm or anything. Like, do something small. Like, find a way to... find a way to calculate the areas under curves or something like that. You know, looking for logical... I don't even know. But, just find some sort of project that's going to, like, ask you to do something that is beyond your skill level, but not, like, tremendously beyond your skill level. Also, recognizing what is just beyond your skill level and not completely way outside is a valuable skill. Because you can say, like, eventually I will know how to do this, and I can look it up, and I can figure it out. Sure. If, like, for instance, me starting my whole brand new computer on Linux may have been a mistake. Like, I'm having some fun with it, but at the same time, sometimes it's a nightmare. There are times when I just wish that I could, pay Microsoft to just deal with it. But at the same time, like, I don't want to. I want to learn to be able to figure out all this stuff. So I've got, like, all these console commands that I'm learning about and trying to figure out. It's working out. It's not super great, but, I'm certainly better than I was 2 weeks ago. superseded this. All right, the only other possibility. That's not true. There are three possibilities, right? We got 3, 4, 5 going like that. We've got 3, 5, 4 going like that. Really? Not going to correct that one, but you'll correct the other one. Okay, so we get 3, 5, 4 like that. And we've got 4, 5. No, that's not. Nope. 3, 5. So these are the three setups that we got. This one has a distance of 8 and a distance of 9. So again, this is distance of 8. Must be less than or equal to that. Again, here, less than or equal to 9 is just superseded. And here, less than or equal to 7, less than or equal to 8. So 8 is superseded. So each of these things puts a different circle at the, center corner. So the one that's in between the other two. Any other arrangement is just going to be the same as one of these. It's just that it's going to be rotated, it's going to be flipped, something like that. So these are the three unique setups. Okay. So with that, so within that, we're always going to have we're always going to have this S and S and S root 2 individual triangle. S being the side length of the square. right? And then P can be anywhere inside the inside the square. So that's half the square. So, because it's being triangulated essentially, there should only be one possible solution for each arrangement, in theory. Right? Yeah. Yeah. Because if this were to go through here, for example, oh, that's not okay. This is fine. Okay, so let's just assume that this is actually to scale. So any two circles are only ever going to have two intersection points as long as their centers are not the same point. So 4 and 5 will match up at this point here and this point here. 3 and 4 will match at this point here and some other point. So there's only ever one solution for each of these arrangements. Okay. So that's good. So this is another skill that is going to be much more important in mathematics than actually calculating the result, and that is knowing what kinds of solutions to expect in the first place. So the sorts of things that we should expect, again, are going to be that we want to figure out how many different arrangements there are, and then once we have those arrangements, we want to know how many different solutions could there be on each one. In terms of circles, there can only possibly be one, because each pair of circles has two unique locations where they can connect, and then those two locations cannot be the same for both sets of circles. Alright, I'm feeling good about it. So alright. So we can see it here a little bit better. Not that it's to scale necessarily, but you get the idea, right? The connections between the 3 circle and the 5 circle are going to be like here and here. The connections, and they lie along this particular line. The connections between the 3 and 4 circle lie along this line. And then the connections between the 4 and 5 circle lie along this line. So these are 3 completely different lines. So there can only possibly be one intersection point where all 3 of them are going to match up. Anyway. Just OCDing, don't mind me. Okay. It's not really that compulsive, but okay. So for each of the arrangements then, what kinds of behaviors exist? Because that's also going to be a good question. We'll go with that. So even being able to draw it out, again, starts looking at this and saying, now we've got a more likely scenario. All right, do we have a lower bound on any of this stuff? I mean 0, but is there a more meaningful lower bound? So with this, right? Now we got to figure out, probably, what are the individual relationships that exist within the triangles, within the circles, or within the square itself. So what kinds of relationships can we pull out from this? All right. Could try to do something stupid here and say, like, if this is 3, this is 4, and this is 5. Oops. Can we construct these triangles using law of cosines? We're going to have two unknowns, the side length and also the angle. But I think this is one of the reasons why it's challenging. Oh, where'd my cursor go? There. Whew. Got me worried for a second. Okay, so if we do this, this says got S root 2. We've got some point P, which allows this to be 3, this to be 4, and this to be 5. So if we split this up into triangles, we got T1, T2, T3. For T1, we've got a theta 1, theta 2, theta 3. S squared is going to be equal to 3 squared plus 4 squared minus 2, 3, 4 cosine theta 1. Okay. S squared from T2 is going to be equal to 4 squared plus 5 squared minus 2, 4, 5 cosine theta 2. And T3 is going to have S root 2 parentheses squared is equal to 3 squared plus 5 squared minus 235 cosine theta 3. And good news, theta 1 plus theta 2 plus theta 3 is equal to 360 degrees, which means that we have 4 equations and 4 unknowns. Might do it. Alright, this is nonlinear, so we're not able to come up with a linear algebra solution. Alright, so we're not going to be able to do matrix methods because it's not linear. That being said, squared is equal to hang on, how does this work? Let's just do this. Alright, 9, 16 minus 234 is going to be 24 cosine theta 1. T2 s squared is going to be 16 and 25 minus 245 is going to be, that's 120 divided by 3 is 40 cosine theta 2. That's probably the harder way to do it. T3 is going to be 2s squared, which is equal to 9 and 25 minus 6 times 5 is 30. And 16 is 25 minus 24 cosine theta 1 equals 41 minus 40 cosine theta 2 is 34 minus 30 cosine theta 3. Cosine 360 minus theta 1 minus theta 2, nope, theta 2, theta 3. Okay. few different possibilities. We can go with either s squared plus s squared is going to be 2s squared, which is then equal, if we add up the two equations up above, add up 1 and 2, that's going to be equal to the third. T1 plus T2 is going to be equal to T3. So that's 25 and 41 is 66 minus 24 cosine of 360 minus theta 3 minus theta 2 minus 40 cosine theta 2. That's going to be equal to 34 minus 30 cosine theta 3. 3. Okay, if we subtract 34 from both sides, this is going to be 32. Then equal to no, 32 minus 24 parentheses. So we're gonna break this down. All right, so subtraction rule, difference rule is this is going to be the cosine of theta 1 this is like alpha minus beta. It's going to be equal to cosine alpha cosine beta plus sine alpha sine beta. So if we do this one step at a time, this is going to be the cosine of 360 degrees. That's alpha. Then minus beta is going to be theta 2 plus theta 3. That's beta. So minus beta. So it's cosine of 360 times the cosine of theta 2 plus theta 3 plus the sine of 360 times the sine of theta 2 plus theta 3. Ooh. This may not work the way I want it to. But that's part of the fun. Alright, is equal to 34 plus 40 cosine theta 2, 2 gerbs. A to the A equals B, very nice. How'd it go? I remember learning about the Lambert W function, but I don't think I could probably tell you what it was. Alright, cosine of 360 is just going to be 1. Sine of 360, on the other hand, is 0, which is then going to take out this thing as well. Okay, maybe my fears are unfounded. Fun. So 32 minus 24 parentheses. This is the cosine of theta 2 plus theta 3. So that's going to be the same as this stuff, just with a minus in between there. So this is going to be the cosine of theta 2 cosine of theta 3 minus sine theta 2 sine theta 3. It's going to be equal to 34 plus, oh, wait, nope, that 34 is not there. Aha, knew something was wrong. Alright, it was 66. I subtracted 34 from both sides. It became 32 on the left. Okay. So it's just these two things, which is now going to be 40 cosine theta 2 minus 30 cosine theta 3. Alright, then here, this is going to be 32 minus 24 cosine theta 2 cosine theta 3 plus 24 sine theta 2 sine theta 3 is equal to 40 cosine theta 2 minus 30 cosine theta 3. Maybe not. Alright, that may or may not do anything. So let's take T1 and T2 and set them equal to each other. Just going to make 25 plus 24 24 cosine of 360 minus theta 3 minus theta 2. And it looks like basically the same thing here, so let's see how this goes. Equals 41 minus 40 cosine theta 2. Right, just that. Here, if we subtract 25 from both sides, we end up with a 16 over here. Move that over there. And negative 24. Okay, so the cosine of this is all the same stuff that we did before. So negative 24 cosine of 360 minus parentheses theta 2 plus theta 3 is going to be equal to this stuff at the end. So negative 24 times the cosine of, nope, theta 2 times the cosine of theta 3 minus sine theta 2 sine theta 3. Okay, and then plus 40 cosine theta 2 is equal to 16. That's not gonna. Not always. But all right, there's an 8 common factor of all this stuff, so let's factor that out. I mean, it might, but I'm not seeing. Oh, you just mean inside of linear algebra? Yeah, cross and dot product do eventually play a role. I thought you meant in this particular problem. In theory, it could, but I'm not sure we need vectors for it. Okay, cosine theta 2 times the quantity, negative 3 cosine theta 3, oops, plus 5. Plus 3 sine theta 2 sine theta 3. I still need to write an email to my colleague. I've been like avoiding it pretty much all week just because at first it was, you know, grades were due in and I was just like, I'm just going to concentrate on this. I'll deal with it later. And then the whole rest of the end of the week was, let's deal with Christmas. You know, kids are all excited and everything like that. So family's in town. So I was just like, yeah, I'll put it off until later. And now it's, you know, 3 days after. 2.5 days after Christmas and still haven't answered this email. It's been a week and change. Yeah, a week and a day since I even received it. Probably longer, now that I'm thinking about it. Hey, Sport Master. So we have a group of points. Sorry, no. We have a square, inside of which is a point P, whose distances to 3 of the diagonals in some arrangement are 3, 4, and 5. So based on that, what are all of the possible different side lengths of the original square? Oops. I keep kicking my other keyboard that's under here. Goodness knows what that's doing on the other system. Honestly, I'll probably have to reinstall the OS anyway. Hey-oh. God, I asked around on the Discords for Ubuntu. I'm like, alright, so seriously, do I just need to reinstall Ubuntu or what? And they're like, well... Can't even give me a straight answer, come on. Alright, I had a reason for doing this. An introduction to systems biology design, principles of biological circuits. Nice. So I don't think it has to be. So here's my arrangement that I created. Or here's one of the three gotcha. Right, so I came up with three arrangements. You've either got the 3, the 4, and the 5, with the 4 in what I call the middle position, or you've got the 5, or you've got the 3 in the middle position. So based on one of those three, we're going to have some arrangement that's going to fit with this stuff. And based on the fact that each of the circle pairs will end up going through 2 points together, right? So they each have 2 points that they cross at. That no matter what the actual arrangement of this stuff is, whoops. Nope. No matter what the arrangement of this stuff is, man. Oh, you thought those were together, did you? Oh, man. Such a mess. Yeah, no, I want to rotate that. That's not going to work. Okay, cool. Undo. Nothing doing. Awesome. Oh no. Oh no. Oh no. Oh, okay. I don't want to erase. That one was fine. Okay. All right, like that. So based on the based on the arrangements of these three differently sized circles and the fact that they are at 3 of the 4 corners of a square, then they're going to be orthogonal to each other here. And then if we dotted this in, there'd be a right angle on each of these corners, but whatever, it's fine. Then the line that connects both of the intersection points between each of the pairs of circles will only intersect at one particular point per arrangement. So with the 4 in the middle, that's our P. With the 5 in the middle, this is our P, which is both still within the square, but outside of the triangle that denotes half the square. So I'm going to end up with this one. Okay, and then, come on, come on, jeez. Same with the 3 over here. It's just now that this is in this particular position. So all 3 pairs end up lining up here. And those should not actually be the exact same location, in theory. These are not to scale and all that stuff, but still. This is still 3. This is still 5. And this is still 4. But now this creates a whole different set of angles. So the angles here that we're dealing with, if we were to do law of cosines, end up being, you know, theta 1's can be the whole thing, and then theta 2, theta 3 can be components of it, which add up to theta 1, rather than adding up to 360. That doesn't really change anything in terms of the algebra, but it's interesting. Okay, and then over here we've got the same thing as the first one, so again, that's 4, that's 3, that's 5. Okay. No, don't do that. We're trying to find the length of S. Oh, I just had a thought here that we could then implement law of sines potentially to to equate some of this stuff. We could get theta 2 and theta 3. To say, what is their product? well, we can't get their product, but we can get, so law of sines is going to say, come on. Why? Law of sines. It's going to say that the sine of theta 1 over s is going to be equal to the sine of theta 2 over s. Oh, interesting. Which is equal to the sine of theta 3 over s root 2. No, no, we can't do that. No. No, 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 no. Wow. Those do not represent individual triangles. Bertram, good job. Hope everything went well. Decent on the calc final. Okay. Well, there's that anyway. Being honest, Sportmaster, I haven't been caring. Lately, it's just been like, look, even, I don't tell anybody, of course, but if anybody's cheating and keeping formulas in their calculator and stuff like that, honestly, it's not going to help them. So most of the time, we just give them the formulas anyway. I don't know what to do with them, so whatever. But hey, you got a B. It's pretty awesome stuff. Yeah, our Calc 2's Calc 2 gets to have like a, I don't know, 4x6 note card or something like that. Same deal. Doesn't actually help. The thing that helps is just doing them over and over and over again. So I was mentioning earlier, tonight's stream title comes from the title of the book Chasing Rabbits by Sunil Singh. And his ideas in terms of mathematics education end up being that we should spend a lot more time focusing on just developing our skills of being mathematicians rather than having to worry about all of the ins and outs of particular skills, because students are just freaking out all the time and not really understanding how to do things. So I don't know. It's a good theory. I just don't know how to implement it. One of the ways that he and his team teacher implemented it in the combo calc physics class was by giving all of their students 12 questions, like a week or two before the exam, and saying, okay, we're going to pick 5 of these. They're going to be on your exam. No guarantee that the numbers will be 100% exactly the same, but, the questions essentially are going to be the same. So, go. And they said it was the most productive week and a half that they had ever seen any group of students have. So they started doing it pretty much from then on. Just because they had so much time to think and sit down and do all of these different problems with different people around the classroom. And I was like, this sounds suspiciously familiar. It's very similar to the Peter Liljedahl stuff. So it's really kind of cool. I'm going to see if I can read more of this, read more of the Peter Liljedahl stuff, and hopefully just get involved. Oh shit, I have a meeting tomorrow. Haven't done a whole lot of work for that. Hey, Brian Andrus, thank you very much for the follow. I am going to grab water and a couple other things, so I will be right back. Yeah, there's always like a trade-off. It maybe I'll read some of the excerpts afterward when I get back. But anyway, like I said, I will be right back. I'm just going to take a quick break here and see y'all in a few minutes. So I'm going to put a 3-minute ad on. Should be fine. See you in a couple. Woo. Yeah, jack of all trades, master of none, of course. But, yeah. Not exactly. So. So I have not actually taught linear algebra myself, but I have taught differential equations, which also includes linear algebra as like one of the sections. And also involves multivariate calculus, which again, I haven't taught that actual class, but no, no, no. Don't put that on me. So let's see. Yeah, so I've got a master's in applied and computational mathematics from Johns Hopkins University. I don't put too much stock in like where I've gone. So Johns Hopkins is a good school and all that. I think I would have gotten like just a fine education practically anywhere. The particular draw of this program is like the people who work at the applied physics lab in Johns Hopkins in their remote campus. Like the people who work there would be able to do their masters at night and also work during the day at their location. Their location is in Laurel, Maryland, which is not near Johns Hopkins University, which is in Baltimore. So my spouse and I both got our masters at this particular location because it was close by, and why not? It's the Johns Hopkins University. Like, it's prestigious. And also, she was going to get it paid for by work, and has since like done enough time working for them to pay it back, and we financed mine. So we ended up, I say we got a 2-for-1 deal. That's essentially how it felt. The program itself, you'll only have to take 10 master's level classes and fill out certain requirements of each thing. You had to do a certain number of 200 level classes, a certain number of 100 level classes, and then you also had to do 2 courses that were in a sequence together in the 200 level. So for applied and computational mathematics, I ended up taking differential equations, statistics at the 100 level, which is like calculus-based statistics, which was just the it was not my favorite class. The teacher did not help it either. Let's see. Combinatorics, which I loved. Again, the teacher was all right, and I do my fair share of ranting about this program. Being somebody who was trained in education, they basically had like untrained professionals who worked at these locations and who were like, decent in a particular field become the teachers for them. And I was like, they're instructors, they're not teachers. There's a very fine line of a difference between them, and most of the people here probably don't care. But somebody who had a degree in education, like, this was not good. So many of the guys who were teaching would come into class and just read off of a PowerPoint or read out of the book or do problems on the board that they had already worked out on a PowerPoint presentation, and I'm just like, oh, no. They were like, yeah, it's the draw of the program. We don't have to have, you know, hoity-toity academic people teaching this. And I'm just like, but you're losing out so much of the academic rigor. Like, and we didn't have to do a master's thesis. So take that on balance, right? Like, I do not have the master's experience of having to do a master's thesis. I never had to write, essentially, anything. I had to write some little papers, but I never had to write, like, you know, a thesis. I didn't have to come up with a project. I didn't have to do all this stuff. So when I got to my institution and they want to, you know, get me promoted to associate professor, which did eventually happen, they were like, yeah, you need to do this project that's like 3 years long, and you've got to have, you know, all these sections of the report. And I'm like, oh no, this would have been so much easier had I ever done a thesis before. But it worked. I eventually got it. It's fine. Anyway, yeah, combinatorics. Nope, neural networks was an excellent class. I loved every second of it. I was also in that class with my spouse, which was both very interesting, very helpful, and at the same time a little bit daunting, because she's just way better at things than I am. Academics in general, you know, being a student, she's just a way better student than I am. That being said, I'm infinitely no offense to her, infinitely better teacher, but she can tutor like nobody's business. So the neural networks class was cross-listed between computer science and applied math, and this is why both of us took it. She did her master's in comp sci, and I did mine in applied math. So it ended up having this nice overlap, and we both looked at each other and said, we're going to study artificial intelligence, essentially, like the basics of artificial intelligence. Yes, please. It was a great class. A lot of linear algebra. A whole lot. So we studied about how the individual neural networks propagate information both downward and backward to fix the neural network. So how machine learning works is essentially you plug in a whole bunch of inputs, and then it filters down through a multi-layer, usually multi-layer, matrix operation that uses linear algebra. And then it gets to the end and it says, well, okay, here's the output, but also here's what the output should have been. So let's compare these two, and the difference between them gets sent backward along all of the layers to say, let's alter how the network calculates this so that next time it'll be better. It's a really great class. It's a really great concept. Let's see. After that, I took matrix theory, which was not great. I didn't particularly spend a whole lot of brain power on it, which I should have, because it could have been a lot better than it was. I could have been a lot better than I was. And then for my other 200 level classes, I took data mining, which was really interesting. Didn't get a whole lot of like application out of it, unfortunately. And see you, Sportmaster. Yep, no problem. I'll see you around later. And oh, right. Partial differential equations and nonlinear differential equations was my sequence. I found those really interesting and wanted to do more. I ended up using a lot of the neural networks that I'd learned to do some programming in differential equations, And so it was, it was kind of cool. It didn't always work the way I wanted it to. My final project for partial differential equations, for example, completely crashed and burned. And I had to go up in front of everybody and say that my project did not work as intended. I still got an A on the project and a B in the class. Because I emailed the professor several times and told him that this was not working and please help me. And he, like, tried helping and he was like, yeah, looks like you're kind of stuck. I don't know what happened. I'm like, great. So I felt like an absolute fool standing up in front of everybody being like, my thing broke. But, you know, he was just like, look, you did what you could. You told the truth. You stood up in front of everybody and it screwed up. So, good job. Which, that's part of working in like in the lab is that you're going to fail and you've got to stand up and you've got to take responsibility for it. So I just told the class that, I emailed the professor and we couldn't figure out what went wrong, but something was very, very wrong. Yeah, there was this one thing that I was trying to do, which was to basically, we were doing like this calculation about seawater flow over a landscape feature, and in particular, how the temperature was affected by this. So this water from down here, which is super cold, ends up hitting this land feature and starts going up, and it creates this like cold spot above the top of the feature, and nobody could figure out exactly why this was. It's off in Strait of Gibraltar somewhere. And so I tried to calculate it out, and the way that we do things in partial differential equations at this point was we take like individual particles and we say that they will affect all of the particles one time step in the future to all four sides and itself. So based on the temperatures of the particles that they're touching, the temperature of the individual particle itself will change. So you do some sort of like vector analysis here of saying like, it's going to be changed a certain percentage by this number, this number, this number, this number, and itself. And one time step in the future, it's going to change like this. Well, I ended up with an entire row of numbers which were like 10,000 degrees. So that's hot. And like, 50,000, 3,800, like just a whole bunch of nonsensical numbers going all the way across. And then up one row from that, now keep in mind, this is like 100 rows tall, right? I've got matrices that are just doing this for days. Up one row, so the particles that are affecting these particles themselves were like negative 20,000. And all this, these were all negatives, these were all positives, these were all negatives. I was just like, man, I don't know what I'm doing. Well, Blaine, then, neither do I all that much. The linear algebra that I have to do, right? The stuff that you do at the, like, sophomore level. has to do with algebra of linear functions. Now, that may be like, well, yes, but the point of this is that this is all dealing with stuff that falls into lines in some way, shape, or form. But it doesn't necessarily tell you how many dimensions it's working in. And that's really the key, is that this is stupidly simple if you're looking at it from just like a 1 or 2 dimensional stance. It's the stuff we've been doing for, years and years. You're saying like, okay, in a 3x3 system of equations, 3x plus 7y minus 8z is equal to 12. 4x minus 10y minus 1z is equal to negative 3, and negative 5x plus, no, not 7, because that's already used. I don't want to do that. 6y minus 4z is equal to negative 50, right? Something like this. You end up getting what's called a linear combination of the individual variables that you have. So you're adding some constant multiple of each of the individual variables in your system to get some sort of result at the end. So the linear combinations in this case can tell you all sorts of stuff about whatever it is that you're working on. The standard ones that we usually talk about are stuff like, adults and kids, tickets are sold to a movie. Adult tickets cost $9. Hint. Yeah, I'm German apparently. Kids are $4. All the people with like clickers come over and they find out that there were 217 people attending, and there was I'm not going to get this, so I might as well just there we go. I might as well not make it up, because otherwise I'm not going to get something that's useful. Let's see, $9 times the number of adults that I think would probably definitely go, plus $4 times the number of kids. There was $1,288 in sales. Ticket sales. So based on that information, can we then figure out how many adults and how many kids were in attendance? So here, this is going to say like A is going to be the number of adult tickets sold. And K is number of kids tickets sold. So the information that we have is telling us that just A plus K, the sum of the two totals, numbers of tickets that we've sold, is going to be 217. And then the total amount of money that we get is $1,288, or $1,288, $1,288. And how do you get that? Well, it's the number of tickets that you sold, A, times the price of each of them, $9, added to all the rest of the groups. So for kids, it's going to be $4 times the number of kids' tickets sold, which is K. So 9A plus 4K is going to be 1,288, and A plus K is 217. Now this could be all sorts of fractional stuff. It can have pi out in front of it or whatever. It doesn't really matter. The point here is that throughout all of this stuff, we've got a linear combination of our variables. Some sort of constant multiple times the variable. You don't see A squared. You don't see A times K. You don't see the square root of something, the square root of A. Again, the square root of 3 would be a perfectly valid value to have. But the thing that we don't have is the square root of A. So all functions of A and of K need to just be basically a linear function, which is it's mx plus b. It's some sort of constant multiple times that particular variable all the way through. All right, so this is then also going to look at like, well, this could represent a vector space. It might not be A and K. It might be, for instance, x1 and x2 as a vector. Right? Here, we could have done this in vector form. This would have said that the coefficients 1, 1, 9, 4 multiplied by, I should have done this first, multiplied by the vector AK is going to get us a vector 217, 1,288. Right, because when you multiply your rows to column, you get that first row, first column, gets the first row, first column. And then second row, first column is going to get a second row, first column. So here, what if we do just a generic vector, x1, x2 instead? Well, this is going to have the same solutions as this. That is not a vector. All the non-Americans are going, what was the problem with that? A, off by 10. B, not actually a comma. Right, in the United States, unfortunately, we use decimal points for separating fractional values from whole values rather than the more sensible comma. So anyway, with linear algebra, what we like to do is then say that we're going to start generalizing this and say that we're going to left multiply our A vector, A matrix, on the left-hand side by its inverse. Well, in terms of matrices, Generically, you can't do commutation of your individual variables. You can only multiply on the left on both sides, or on the right on both sides. The reason that we want to left multiply A inverse times A is that these are inverse matrices of each other. And so we get the identity matrix 2 by 2 multiplied by our x vector, which is going to be equal to A inverse times C vector. Identity matrices end up getting you back the same thing as what you started with, so we just have x vector is going to be equal to A inverse times C vector, which is going to be our constants that we had over there. So linear algebra at its heart is basically the intro to matrix theory, to try to understand how matrices actually work. There's also a reason why oftentimes you're suggested to take linear algebra before you take multivariate calculus. Pretty much for that reason, is that it gets you a whole lot of experience in knowing how all of this stuff allegedly works, how we can work with vectors, and eventually how we can solve equations based on all of these things. All right, so So I would like to read a couple of excerpts out of Sunil's book, which are absolutely genius. I'm going to probably end up reading this whole thing out loud at some point, but anyway. So chapter 2 starts, ready, set, stop. I know the title of this chapter seems to surf some quasi-absurdity reminiscent of all things in Alice in Wonderland. After all, this whole book is about chasing rabbits, right? Isn't that about hustling and bustling while doing math problems and feverishly exploring the enormousness of the mathematical universe? Vast and deep exploration, yes. Accelerated passage, no. The world of mathematics might be as psychedelic as Lewis Carroll's 19th century classic, but our time spent here must be the exact opposite of the frenetic pace set by the White Rabbit. While his I'm late for a very important date might be appropriate in our current K-12 math culture of being overwhelmed, overbooked, overobligated, and just over everything, mathematical chasing has a much different meaning and velocity outside the stress chamber of most schools. Mathematics is more akin to the calmness but purposefulness of a tortoise's strides. Finding that Sunday stroll is also finding the walk of wellness. Why wouldn't we figuratively apply that leisurely and healthy gait to learning mathematics, which could use some fresh air and a slower pace? Now imagine taking this walk into a forest of tall sequoias, aromatic, woodsy scents, familiar and unfamiliar. Flowers, breezes, both felt and heard, and a constant unfolding of new permutations of these gifts. This whole book of thinking about mathematics is devoted to this walk, catalyzed by that day of rest. Mathematics should not be a burden for our students, it should be a balm, the kind that is also supported by sipping coffee, wandering thoughts, a bit of daydreaming, and maybe a nap or two. And his personal story. Here's another shot of absurdity. Unfortunately, math came too easily to me. Too easily? Yes, and I hope you noticed what I emphasized in that sentence. So let's stop and think about that. My easy breezy experience as a student of mathematics was one of those things that caused a severe delay in seeing it through a more colorful and meaningful prism. You see, I rarely got stuck on a problem, especially in how to start it. Every problem I encountered, I had at least some inkling and general understanding of the approaches required. It doesn't mean I solved every problem correctly, it just means that I never got stumped to a meaningful degree of drawing a blank after blank after blank, which means I rarely encountered dead ends, unlit paths, or red lights, long red lights in my math problems. Answers were always nearby. It was generally a smooth downhill road of flashing green with no significant stops. A constant, fun roller coaster drop with my jubilant hands in the air. However, in an ironic twist, probably choreographed by the cosmos, my success as a student would partially set me up well for failure as a math teacher, and inability to see the full spectrum of the higher purpose of learning mathematics. My lens was the epitome of the absurd. It was both too clear and too cloudy at the same time. Exiled from struggle, my brain was not wired for patience, for irresolution. Regrettably, some of my teaching career would carry this baggage of success. So, I hope at some point we can come back, kind of look at this stuff and just struggle with it for a while. That was my intention. And even before I did any of the Amatic stuff, like earlier this year, we broke into Mathematic Educator, into the problems in the back, and discussed how to try to solve a couple of them that were here. They give us a series of interesting problems. A series of interesting problems that are to be solved, and these were given in spring, so like April, and let's see. Please send proposed solutions by email to the solutions editor. And there was a date on this. I thought it said like for January. Oh well. But we worked on one that was pouring liquid out of a cylinder, or rather trying not to pour liquid out of a cylinder. We're trying to like tip it as far as it would go before finally letting some out and saying how much of the yeah, there it is. Glass of radius capital R and height capital H is at least half filled, holding an incompressible liquid at height little h with big H2 less than or equal to little h less than or equal to big H. So just our little h is somewhere between the halfway and full mark of the cup. It is tilted slowly so that the angle alpha between the vertical and the axis of the glass slowly increases. So from 0 to 90, we're just going to increase the angle. Find the size of the angle alpha at which the liquid begins to spill in terms of little h. So we were able to solve this. I don't even remember when it was. I don't have it in my whiteboard stuff here, which is kind of slightly aggravating. I was looking for it to try to type up the solution. Now I can't find it. But the idea was that it is related directly to h, and that h value is identical in any number of dimensions. So we could simplify this to a two-dimensional system. We're just saying that the water is flat against this two-dimensional surface, and then as we tip the glass, the water is going to stay flat. So look at it as a two-dimensional problem. A cylinder becomes a rectangle. So you're just tilting a rectangle. At what point does the water reach the edge of this thing? Well, that's at a certain angle. We figured out what that angle was. It was really cool. But this was also kind of the thing, right? If we come across random problems like this, we're much more likely to be interested in these sorts of things and to try and understand how mathematics works. It's really important. Okay. So let's go find somebody who's doing something. 100%. Scott Manley is doing some X-Plane 12. Lynn Marley's doing some Fallout 76. Dev is still around, but I think he's probably gonna be logging out pretty soon, so I'm going to be leaving him alone. No offense, Dev. I just get the feeling that he's about to raid out. So let's go see Scott Manley, because he does some really awesome stuff. All right, here we go to go see Syzygy. I hope I can see everybody on Friday for some games. I will have the new system hooked back up again, and probably play more Astroneer. I don't know what else we're gonna do, but we'll see something. We'll probably try to throw another game in there and see how it works. I'm still trying to get a bunch of the Epic games working, and I'm trying to catch back up on Final Fantasy VII Remake to getting past Don Corneos. So, everybody have fun. I'll see you later. This is Obi-Wan Pez for Ensign Pachinko. Have a good night.